Have you ever played the game of telephone? You whisper a message, it's passed through a line of people. By the end, it barely sounds like what you started with. In AI systems, that same problem can break everything. Every AI you use, GPT, Cloud, Gemini, moves information through hundreds of layers. Two things can go wrong. Signals grow too strong or slowly fade away. Engineers solve this with residual connection. The original message always has a clear path forward. No fading, no explosion. That balance is why modern AI works. But the researchers want more. What if that path could learn? That idea leads to hyperconnections. Models improve, but the balance broke. The signal that should stay at one grew to thousands. Training crash, resources wasted. Then DeepSeek introduced mHC. Simple rule, learning is allowed, but average signal stays the same. Signal grows dropped from thousands to 1.6. Stable, reliable, and scalable. In the next few minutes, I will show you exactly how this works. Let's dive in. Let's dive in.
Remember that telephone game? Here's why AI doesn't lose the message. For over a decade, one simple idea has powered every major breakthrough: image recognition, language models, the AI writing your emails right now. It's called the residual connection. Here's how it works: information comes in, it passes through a layer that transforms it, learns from it. But, and this is the key, the original information also gets a direct shortcut, a clean path forward. Then both are combined. Why does this matter? Modern AI models have hundreds of layers, sometimes thousands. Without this shortcut, the original message would fade. Layer by layer, it would disappear into mathematical noise, just like the telephone game. The residual connection guarantees that what you put in at the start can still be heard at the finish. Engineers call this the identity mapping property. It's not glamorous, but it's the reason AI works at all. So the system worked, but researchers wanted more. They asked a dangerous question. What if that shortcut could learn? What if instead of just passing information through, it could decide how to pass it? That's hyperconnections. Think of it this way. The original design was a single lane road, safe, reliable, but limited. Hyperconnections upgraded it to a multi-lane expressway. Now you have 4 lanes instead of 1, maybe more, and each lane can talk to the others. There's a controller that decides what enters the processing layer. They called it H-pre. Another that decides what comes out, H-post. And the most important one, H-res, that mixes traffic between all the lanes. This was exciting. You could increase capacity without increasing computation cost. More information flowing, same energy spent. The models got better, but something else was happening. Something nobody saw coming. Here's what nobody expected. Remember that identity mapping? The guarantee that signals flow through cleanly? Hyperconnections broke it. Not intentionally, not obviously, but completely. That H-res controller, the one mixing traffic between lanes, it had no rules. It could do anything: amplify signals, suppress them, scramble them entirely. And when you stack dozens of these controllers on top of each other, they multiply. One controller slightly amplifies, the next one amplifies that amplification, layer after layer. What starts as a whisper becomes a scream, or what starts clear fades to silence. The most powerful component became the most dangerous. Now, let me show you what this looks like in practice. These are real experiments. 27 billion parameter models, the kind that cost millions to train. On the left, training loss over time. Blue line is the fix we'll discuss soon. Gold line is original hyperconnections. Watch what happens around step 12,000. The model is learning fine. Loss is dropping. Everything looks good. Then, spike. The loss surges. Training destabilizes. Progress erased. On the right, gradient norms. These tell the model how to update. With the fix, they stay calm, predictable, flat. With hyperconnections, look at those swings. Spikes reaching 4, 5 times higher than normal. Researchers measured worst-case signal amplification. The ideal value is 1. The actual peaks, nearly 3,000. 3,000 times amplification. This isn't abstract math. This is a training run that took weeks crashing. This is compute that cost hundreds of thousands of dollars wasted. This is a team watching their work unravel in real time. The telephone game again. The message didn't just get distorted, it exploded. So how do you fix this? This is where mHC comes in. Manifold-Constrained Hyper-Connections. The insight is simple but powerful. Don't remove the learning, just add rules. Remember HRES, the controller that went haywire? Instead of letting it do anything, constrain it to a specific mathematical space. Think of it like this. Before, HRES could turn the volume to any level, whisper, normal, deafening. Now, it has to keep the average volume the same. It can still mix signals between lanes. It can still learn, but it can't amplify and it can't suppress. The technical term is doubly stochastic matrix. Every row adds up to 1. Every column adds up to 1. What does that mean practically? When HRES mixes your signals, it's not amplifying or reducing. It's redistributing. Like pouring water between cups, the total amount never changes. The result? Feature mean is conserved. Signal norm stays bounded. No explosions, no vanishing. The telephone message gets through, but you still get the learning. You still get the multiple lanes. You just get them with guardrails. Let's see if it actually works. Same model, 27 billion parameters. Same training setup. With hyperconnections, signal gain ranges from 1 to 10,000. Wild oscillations across every layer. With mHC, it stays between 1 and 2. Flat, stable, controlled. mHC reduces maximum signal gain from 3,000 to 1.6. That's not a percentage improvement. That's 3 orders of magnitude. That's the difference between a message that arrives intact and one that shatters into noise. Now, does stable mean better? Let's look at results. Training loss over 250,000 steps. Gray line, standard approach, ends around 0.4. Gold line, hyperconnections. It actually gets worse. ends at 0.6. All that instability hurt learning. The model trained longer, but learned less. Blue line, mHC, keeps dropping, ends at negative 0.021 relative to baseline. Better performance, stable training, both. The gradient norm chart tells the same story. Hyperconnections has spikes hitting 600. mHC stays flat, calm, predictable. Now the benchmarks. BBH tests reasoning. Can the model think through complex problems? mHC 51.0. Hyperconnections 48.9. Standard 43.8. Drop test reading comprehension. Can it understand and extract information? mHC 53.9. That's 2.3 points above hyperconnections. Math problems, general knowledge, common sense. mHC wins across the board. And these results hold from 3 billion parameters to 27 billion. Scale your model, scale your data. mHC keeps delivering. This isn't marginal. This is what happens when training actually works the way it's supposed to.